In this lecture, we will continue our discussion on Poisson point processes, focusing on some of their key properties. We'll start by introducing the Laplace functional. Let's consider script x, which is our familiar d-dimensional Euclidean space, R to the d. Recall that for a simple point process, S, which maps from omega to script x raised to n, all the random points are unique. Because of this, we can also think of S as a set of countable points within the space script x. Let n mapping from omega to z plus raised to script b of script x be the counting process that is associated with this simple point process S. As a reminder, we can observe that the differential dn of x is 0 for all x that are not in S, and dn of x is a Dirac delta at x times the indicator that x is in S. Therefore, for any Borel measurable function, f mapping from script x to R, and any bounded set A in script B of script x, the integral over x in A of f of x dn of x is simply the sum of f of x for all x that are in the intersection of S and A. Now let's define the Laplace functional. The Laplace functional denoted script L sub s maps from the space of non-negative functions on script x r plus raised to script x to the non-negative real numbers r plus. For a point process S and its associated counting process n, the Laplace functional is defined for all non-negative Borel measurable functions f mapping from script x to r plus as script L sub s of f is the expectation of e to the power of minus the integral over r to the d of f of x dn of x. A quick reminder on this: if f is a simple function, say f equals the sum from I equals 1 to k of ti times the indicator function of ai, then we can write the Laplace functional as a function of the vector t1, t2, and so on till tk. In this case, the script L sub s of f becomes the expectation of e to the power of minus the sum from I equals 1 to k of ti times the integral over ai of dn of x. This simplifies to the expectation of e to the power of minus the sum from I equals 1 to k of ti times n of ai. We can observe that this is in fact the joint Laplace transform of the random vector n of a1 and so on till n of ak. In this way, one can compute all finite dimensional distributions of the counting process n. Now, a proposition regarding the Laplace functional of a Poisson point process. The Laplace functional of a Poisson point process, S mapping from omega to script x raised to n with an intensity measure lambda mapping from script b of script x to r plus when evaluated at any non-negative Borel measurable function, f mapping from script x to r plus is given by script L sub s of f equals e to the power of minus the integral over script x of 1 minus e to the power minus f of xd lambda of x. Let's start the proof of this proposition. For a bounded Borel measurable set A in script B of script x, let's consider a truncated function g defined as f times the indicator function of A. Then the Laplace functional script L sub s of g is the expectation of e to the power of minus the integral over script x of g of x dn of x. This is equivalent to the expectation of e to the power of minus the integral over a of f of x dn of x. Clearly, since dn of x is delta sub x times the indicator that x is in S, we can write script L sub S of g as the expectation of e to the power of minus the sum for x in S intersect a of f of x. We know that the probability of n of a, which is the cardinality of S intersect a, being equal to n points in the set A, is given by the Poisson probability. Probability P that n of a equals n is e to the power minus lambda of a times lambda of a to the n divided by n factorial. Continuing the proof, given that there are n points in set A, the joint density of these n point locations, say x1 through xn, is given by the product from I equals 1 to n of d, lambda of xi divided by lambda of a times the indicator that xi is in A. This is because conditional on n of a equals n. The points are I by I with distribution lambda restricted to a and normalized. Hence, we can write the Laplace functional script L sub S of g as e to the power minus lambda of a times the sum over n in z plus of lambda of a to the n over n factorial times the product from I equals 1 to n of the integral over a of e to the power minus f of xi d lambda of xi over lambda of a. After some algebraic manipulation, this expression simplifies to e to the power of minus the integral over script x of 1 minus e to the power minus g of xd lambda of x. The full result for f over the entire space script x then follows by taking an increasing sequence of bounded sets ak that converge to script x and applying the monotone convergence theorem.
Next, let's discuss the superposition of point processes. Suppose we have a sequence of simple point processes, S superscript k mapping from omega to script x raised to n, each with its own intensity measure lambda k and counting process nk for each k in the natural numbers. The superposition of these point processes S superscript k for k in n is defined as a new point process S, which is simply the union of all S superscript k.
As a reminder, the counting process associated with this superposition S is given by n, which is the sum of all n k. And by the monotone convergence theorem, the intensity measure of the superposition S, denoted lambda, is the sum of all lambda k. Another reminder, the superposition process S is simple if and only if the sum of nk is locally finite, meaning n of a is finite for any bounded set A. Now for a theorem regarding superposition, the superposition of independent Poisson point processes S superscript k for k in n with respective intensities lambda k for k in n results in a Poisson point process with an intensity measure equal to the sum of lambda k if and only if this sum of lambda k is itself a locally finite measure. Let's look at the proof. Consider the superposition S equals the union of S superscript k, where each S superscript k is an independent Poisson point process with intensity measure lambda k. We will focus on proving the sufficiency part of this theorem. So we assume that the sum of lambda k is a locally finite measure. It is clear then that n of A, which equals the sum of nk of A, is finite for all bounded sets A in script B of script X due to this local finiteness assumption. In particular, this means that dn of X equals the sum over k of dnk of X for all X in script X. Using the monotone convergence theorem and the independence of the counting processes nk, we can write the Laplace functional for the superposition S script L sub S of F for a non-negative Borel measurable function F as the expectation of e to the power minus the integral over script x of f of x times the sum over k of dnk of x. Due to independence, this becomes the product over k of script L sub S superscript k of f. Substituting the known form of the Laplace functional for a Poisson process, this equals e to the power of minus the integral over script x of 1 minus e to the power minus f of x times the sum over k of d lambda k of x. This is the Laplace functional of a Poisson process with intensity sum of lambda k. Now let's turn to the thinning of point processes. Consider a probability retention function p, which maps from script x to the closed interval 0.1. Also imagine an independent Bernoulli point retention process y mapping from omega to the set 0.1 raised to script x such that the expectation of y of x expectation y of x is p of x for all x in script x. The thinning of a point process S with this probability retention function P is a new point process S superscript P defined as the set of points Sn from S for which y of Sn equals 1. Here, y of Sn is an independent indicator for the retention of each point Sn, and the expectation of y of Sn given Sn is P of Sn. We have a theorem for thinning. The thinning of a Poisson point process S from omega to script x raised to n having intensity measure lambda with the retention probability function P from script x to the closed interval 0.1 yields another Poisson point process S superscript P. Its intensity measure lambda superscript P is defined for all bounded A in script B of script x as lambda superscript P of A equals the integral over A of P of x d lambda of x. Let's look at the proof of this thinning theorem. Let A in script B of script x be a bounded Borel measurable set, and let f from script x to r plus be a non-negative function. Let n superscript p be the counting process associated with the thinned point process S superscript p. Hence, for any bounded set A in script B of script x, n superscript p of A is the sum over x in S intersect A of y of x. That is, dn superscript p of x equals delta sub x times y of x times the indicator that x is in S. Therefore, for any non-negative function g of x, which we can write as f of x times the indicator that x is in A, the integral over x in script x of g of x dn superscript p of x equals the integral over x in A of f of x dn superscript p of x. This in turn is the sum over x in S intersect A of f of x times y of x. Continuing the proof, we can write the Laplace functional of the thinned point process S superscript P for our non-negative function g of x, which is f of x on A and 0 elsewhere, as script L sub S superscript P of G equals the expectation of E to the power minus the integral over A of f of x dn superscript P of x given n of A. This can be expanded as the sum over n in z plus of the probability that n of A equals n times the product from I equals 1 to n of the expectation of e to the power minus f of Si times y of Si given Si is in A. The first equality follows from the definition of the Laplace functional and the law of total expectation, nested expectations. The second equality follows from the property that given n of A equals n, the n points Si within A are IID, as per the properties of Poisson processes discussed previously, specifically regarding their conditional distribution. Since Y is a Bernoulli process independent of the underlying process S, and the expectation of Y of Si is P of Si, we get the expectation of e to the power minus f of Si times y of Si given Si is in S intersect A equals the expectation of e to the power minus f of Si times P of Si plus 1 minus P of Si given Si is in S intersect A. Here, if y of Si equals 1 with prob P of Si, we get e to the power of minus f of Si. If y of Si equals 0 with prob 1 minus P of Si, we get e to the power of 0 equals 1. From the known distribution of points for a Poisson process S, which is d lambda x by lambda of A for x in A, given n of A equals n, we can then write script L sub S superscript P of G as e to the power minus lambda of A times the sum over n in Z plus of 1 over n factorial times the integral over A of P of x e to the power minus f of x plus 1 minus P of x d lambda of x all raised to the power n. The sum neatly telescopes into an exponential form e to the power of minus the integral over script x of 1 minus e to the power minus g of x times P of xt lambda of x. The result for a general non-negative f over the whole space follows by taking an increasing sequence of sets ak converging to script x and using the monotone convergence theorem. This is the Laplace functional of a Poisson process with intensity measure P of x d lambda of x. This concludes our lecture on superposition and thinning properties of Poisson point processes.